Hello everyone. Today we're going to learn in multivariable calculus how to do the equivalent of U substitutions that you know from single variable calculus. How to do the equivalent of that in multivariable calculus. Okay, what is the idea? The idea is that we want to do a double integral in x and y over this region R, which is not a very nice region. We'd much rather integrate over a region that looks like this one, G. It's a nice rectangle. Much easier. Your bounds on your double integrals are just numbers. Here they might be some very complicated functions. This is generally going to be what we want. So how do we go from here to here? We do a transformation of the variables x and y to the variables u and v. In single-dimensional or single-variable calculus, we simply do a transformation from x to u, where presumably the integral with u in it is much nicer than the integral with x in it, and often we find that the bounds in u are easier than the bounds in x. So this is just the multivariable equivalent of doing that kind of transformation. Okay, a result we're going to use from more advanced calculus classes than this one is the following. A double integral over the region R of some function of x and y, dx dy, equals a double integral over the region G as long as I replace x with the equivalent x of u and v and y of u and v. I'm going to have du dv out here. The extra thing I'm going to have is what's called the Jacobian. And here I put the absolute value of the Jacobian. What is this Jacobian thing? Well, it's a little bit complicated. I'll put it up here. It's the determinant of the partial derivative of x with respect to u, partial derivative of y with respect to u, partial derivative of x with respect to v, and the partial derivative of y with respect to v. And we're going to need to take the determinant of that. It's a little complicated, but hopefully when we do an example, it won't be so bad. The first thing we're going to have to do, of course, is calculate the transformation and then take these partial derivatives. Take that determinant, that's what goes in here. So that's really the only extra piece. Of course, these bounds here are very different than the bounds here, right? Hopefully, these bounds are much simpler than these bounds. Okay, let's do a concrete example. This will make things a lot clearer, I hope. Okay. So here's our region R, which we're going to do a double integral over. And this is not really a nice integral, right? You notice that the region R, if you do, whether you do a vertical type of stripe or a horizontal type of stripe, you're actually going to have to do two integrals because the functions change on the boundary, no matter which way you do it. Hopefully we can transform this using a transformation that I'm actually going to give you. They're right down here. Here's u as a function of x and y, and here's v as a function of x and y. Hopefully that's going to make this region R turn into a much nicer region in the UV plane. Okay, the first step in these problems is to solve these two equations for x and for y. We're going to need those. We're going to need that up here in the Jacobian, right? We need to take the derivative of x with respect to u and v, and same thing for y. But we're also going to need these the values for the solutions for x and y as we map what this region looks like in the UV plane. This is not so hard. In fact, you can see if I add these two equations, right, the y is going to drop out. Let's do it. U plus v equals, I've got a 1/2 x here, 1/2 x here. The y's are going to drop out. I'm just adding those things. So u plus v is equal to x. Therefore, x is equal to u plus v. Let's do the same thing for y. You can see that if I subtract v from u, the x's are going to cancel, and the y is not going to cancel. So let's do that. U minus v equals, okay, the x's cancel. I get 1/2 y minus 1/2 y. Well, I just got y. So y is equal to u minus v. That's really nice. That's a nice pair of equations there that we can use to figure out what this region R looks like in the UV plane. All right, let's go to it. Magically in the next page, I have pretty much exactly what we just did. Here's our region R. We want to know what is this going to look like in the UV plane. This is going to define the bounds of our UV integral. Okay. Generally, you want to keep track of the sides of the region R. In this case, we've got 3 sides that we need to worry about. We're going to try to transform each one of these sides separately into another segment, another boundary region over here. Okay, so let's do it. Okay. Segment number A. A is this line. What is this line? Well, it goes from the origin to the point 2, 2. What is that line in the xy plane? It's just the line y equals x. Okay. What range of x values are we covering for that line segment? It's just from 0 to 2. This is kind of important, so make sure you write that down along with your equation for your line segment. X goes from 0 to 2. Okay. All right. Now, if y equals x, let's substitute using our equations that we found. Substitute for y, u minus v. Substitute for x, u plus v. And we're going to get u minus v equals u plus v. Well, you can see if that's true, the u's cancel and I get minus v is equal to v. Well, there's only one way that's possible. V must equal 0. What does that mean? That means that the line y equals x in the xy plane, given this transformation, that's going to convert, this transformation is going to convert this line into this line. This is an even simpler line. Now, one problem you might know is, okay, this is actually an infinite line. This is actually a line segment, so u must only be a certain range of values, because this is the entire u-axis. But we know we're going to get a line segment. So we need to figure out what values of u we actually get. Well, look at this. If v is equal to 0, then I can put 0 in here for v, and I just get x equals u. Well, that's kind of nice. If x goes from 0 to 2, that must mean that, that must mean that v also goes from 0 to, that must mean that u also goes from 0 to 2. So we actually have a piece, right? This piece A corresponds to this piece right here. U goes from 0 to 2 and v equals 0. Let's actually put that in up here. And we'll use orange. So v is 0 and u goes from 0 to 2. That's this thing right here. Maybe I'll put a couple dots there. Okay, this is piece A. Okay. Let's tackle piece B next. Okay, B, let's see, it's got a slope of -1, right? And, well, let's just use the point slope form to figure out what the equation is, right? It goes through 2, 2, and it has a slope of -1. So B, y minus 2 must be minus, that's the slope, x minus 2. Okay, so that's just equal to minus x plus 2. So solve for y, and I get y is equal to minus x plus 4. Okay, there we go. Now, what values of x does this correspond to? It's just the values from 2 to 3. Okay, so I'm going to put that down here. x goes from 2 to 3. Looks good. All right, so we have to convert this into a u and v equation, both of these things really. Both the equation and the restriction on x, we have to convert that into u and v. We're going to do the same thing we did before, which is I use my equations for x and y, plug them in there, see what I get. So y is equal to u minus v, x is equal to u plus v, so that's minus u minus v plus 4. Okay, I've got a minus v on both sides, right? Minus v there, minus v there. That's going to cancel. I'm going to bring this over. I'm going to get 2u is equal to 4. Therefore, u is equal to 2. And that's our result for this segment. So this line, y equals x minus x plus 4, corresponds to the line u equals 2. Now, once again, that's an infinite line. So we have to figure out what are our restrictions on v. Well, let's look up here. Okay, if u is equal to 2, then x must be 2 plus v, or v is equal to x minus 2. Right, so v is equal to x minus 2. Right? I can just subtract 2 from these values. So v must go from 0 to 1. Okay, this line with this restriction corresponds to u equals 2, v goes from 0 to 1. Let's put that in our graph. U equals 2. That's this nice vertical line right here. Get it as close as I can there. Okay, there's the 0.21. Okay, that's segment B. You can kind of guess, right? You can kind of guess. We know this is a closed region. This will map to another closed region. It's actually pretty easy to guess at this point that segment C here is going to be the line going from here to here. Okay, let's see if that's the case. Okay. Segment C, here we go. Okay, going back up to my graph, right here, what is the equation of this line? It looks like it has a slope of 1/3 and it goes to the origin. So y must equal 1/3 times x. Okay, let's plug in what we know for y and x using our nice little things up here. X is u plus v, y is u minus v. You're probably getting used to this by now. U minus v equals 1/3 u plus v. Okay. Well, okay, that's not quite as nice, but that's not so bad. This is 1/3 u plus 1/3 v. Right. So it looks like I'm going to give myself a little more room here. Just zoom over here. Okay, I'm going to bring the 1/3 u over to the other side. What would that get me? 2/3 u. And I'm going to bring v over to here. That's going to get me 4/3 v on that side. Okay, so let's solve for v. Just multiply both sides by 3/4, and I get v is equal to u over 2. Okay. So this line, y equals 1/3 x, corresponds to v is equal to u over 2. Let's see if that matches what we thought. Yeah, the line from here to here, right, has a slope of 1/2. So in fact, that is right. We've confirmed that this is the final piece. Let's mark that with C. Now we didn't really confirm that. I mean, as an exercise for you, you can decide, okay, remember this only works for x, right, going between 0 and 3. And so I should have written that down, right? X goes between 0 and 3. You should try to confirm for yourself that if this is true, then u only goes between 0 and 2. You can try that for yourself. Well, we're done. We're essentially done. We just converted this region R, kind of a nasty region, into a much nicer region, which I think is usually called G. So instead of doing a double integral over this region, we're going to do a double integral over this region. Now we're not actually going to do a double integral. Remember our formula over here. Right? I didn't give you a function, but in principle, from this point, you could actually do it. The only thing that we're missing is this Jacobian. Okay, why don't we do that right now? Here's the Jacobian. It's going to be the determinant of dx du. Now, if you remember, x is u plus v, so dx du is 1, and dx dv is 1. So dx du is 1, dx dv is 1. Kind of looks like a y up there. Let's make sure it's an x. dy du, y is u minus v. I'm trying to do this one. Y is u minus v, so this is also 1, and dy dv is minus 1. So I do this determinant, and you're going to get minus 1 times 1. Right? Remember, it's this one times this one minus this one times this one. You get minus 2. Okay? So kind of our final result, let's go down here where can we write this? How about the very bottom here? Our final result is this. If we wanted to integrate over that region R, some function, then instead we can do an easier integral over the region G, okay, as long as I multiply by the absolute value of the Jacobian, which is going to be 2 du dv. Difficult integral, easier integral. Because remember, in this case, G is a nice triangle. Right? You've done double integrals. By this point, you should have done double integrals over regions like this. This is not so bad. And that's it. That's our final result, and I hope you enjoyed the lesson.